Welcome to Sleepy Science Post, where we explore the wonders of our planet in the most soothing way possible. Tonight, we invite you to drift away on a gentle journey through one of Earth's most magnificent processes, plate tectonics. Over the next 2 hours, we'll explore how our planet breathes, moves, and transforms itself with the patience of deep time. Let the slow dance of continents carry you into peaceful slumber. Close your eyes and imagine the Earth, not as a static sphere, but as a living, breathing entity. Beneath the ground you walk on, beneath the deepest oceans and the tallest mountains, something remarkable is happening. The very surface of our planet is moving, has always been moving, in a dance so slow and so grand that a human lifetime captures barely a whisper of its rhythm. This is the story of plate tectonics, a tale told over hundreds of millions of years, where continents drift like rafts on a hidden ocean, where mountains rise grain by grain, and where the Earth constantly reinvents itself. Let this ancient story carry you gently into rest. Fact 1. The lithosphere, Earth's gentle shell. Our story begins with the lithosphere, the cool, rigid outer shell of Earth that wraps around our planet like a blanket. This layer extends down about 100 kilometers beneath your feet, a thin skin on a vast sphere. Unlike the deeper, hotter layers below, the lithosphere is solid and brittle, floating serenely on the more fluid layer beneath. Imagine it as the delicate crust on a pot of honey, peaceful and still on the surface while warmth flows slowly underneath. Fact 2. The asthenosphere, the layer of flow. Directly beneath the lithosphere lies the asthenosphere, a layer of rock so hot it behaves like thick syrup over geological time. This isn't a liquid sea, but rock that flows imperceptibly slowly, moving just a few centimeters each year. The asthenosphere extends from about 100 to 400 kilometers deep, and its gentle, viscous flow is what allows the plates above to glide and drift. Picture honey warming in sunlight, thick but yielding, supporting but allowing movement. Fact 3. 7 major plates, the planetary puzzle. The lithosphere isn't one continuous shell but is broken into 7 major tectonic plates that fit together like an ancient, three-dimensional jigsaw puzzle. These are the Pacific Plate, the North American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, the Indo-Australian Plate, and the South American Plate. Each one is vast beyond comprehension, carrying continents and ocean floors on journeys that span millions of years. Fact 4. Dozens of minor plates, the supporting cast. Alongside the 7 major players in Earth's tectonic dance, there are many smaller plates, fragments that fill the spaces and create complexity in the grand pattern. Plates like the Arabian Plate, the Caribbean Plate, and the Philippine Sea Plate each play their part in the slow choreography. Some are as small as a few hundred kilometers across, moving and rotating in their own gentle rhythms between their larger neighbors. Fact 5. Continental plates, the ancient rafts. Some plates carry continents, those familiar landmasses we call home. Continental crust is ancient and light, composed primarily of granite and other light-colored rocks that are less dense than the ocean floor. This buoyancy is why continents sit higher, rising above sea level. They are between 30 and 70 kilometers thick, deep roots supporting the land where life flourishes, where forests grow and rivers run. Fact 6. Oceanic plates, the younger travelers. In contrast, oceanic crust is denser, younger, and thinner than continental crust, typically only 5 to 10 kilometers thick. Composed mainly of dark basalt rock, oceanic plates form at mid-ocean ridges and are constantly being renewed. No oceanic crust on Earth is older than about 200 million years, a mere moment in geological time, because it's continuously recycled back into the Earth's interior. Fact 7. The speed of drift slower than growing hair. The movement of tectonic plates is measured in centimeters per year, roughly the same rate at which your fingernails grow. The fastest moving plates travel about 10 centimeters annually, while the slowest barely move 1 centimeter. Over a human lifetime, a plate might move just a few meters, but over millions of years, these tiny movements accumulate into journeys of thousands of kilometers. Fact 8. Convection currents, the hidden engine. What drives this slow dance? Deep within Earth's mantle, heat from the planet's core creates convection currents, like the gentle circulation in a pot of thick soup warming on a stove. Hot rock rises slowly toward the surface, cools, and then sinks back down in an endless cycle. These currents, moving just millimeters per year, drag the plates above along with them, patient and persistent. Fact 9. Heat from the core, Earth's ancient fire. At the center of our planet lies a core as hot as the surface of the sun, reaching temperatures of about 5,400 degrees Celsius. This heat is both primordial, left over from Earth's formation 4.6 billion years ago, and radiogenic, continuously generated by the decay of radioactive elements. This warmth, radiating slowly outward through thousands of kilometers of rock, is the fundamental energy source for plate tectonics, a fire that has burned steady for eons. Fact 10. 3 types of boundaries, the meeting places. Where tectonic plates meet, 3 different scenarios can unfold, each creating its own unique geological features. At divergent boundaries, plates pull apart. At convergent boundaries, they push together. At transform boundaries, they slide past each other. These meeting places are where Earth's most dramatic geological processes occur, though even here, the pace remains measured in human terms, sudden only on geological timescales. Fact 11. Divergent boundaries, the places of birth. At divergent boundaries, plates slowly separate, and new crust is born in the gap between them. This is where the Earth quite literally creates new surface. As plates pull apart, hot magma from the mantle rises to fill the space, cooling and solidifying into fresh oceanic crust. It's a process of gentle creation, of renewal, happening continuously beneath the ocean waves. Fact 12. Mid-ocean ridges, the longest mountain chains. The most extensive mountain ranges on Earth aren't the Himalayas or the Andes, but the mid-ocean ridges, underwater mountain chains that stretch for over 65,000 kilometers around the globe. The mid-Atlantic ridge runs down the center of the Atlantic Ocean like a spine, marking where the Eurasian and North American plates separate from the African and South American plates. New ocean floor emerges here, spreading outward at a pace of a few centimeters each year. Fact 13. Rift valleys, continents beginning to part. sometimes divergent boundaries occur within continents, creating rift valleys where the land slowly tears apart. The East African Rift is one such place, where the African plate is gradually splitting into two. Over millions of years, this rift will widen, and eventually, seawater will flood in, creating a new ocean basin. For now, it's a valley, a series of lakes, a place where the earth is slowly, peacefully opening. Fact 14. Convergent boundaries, the meeting of giants. At convergent boundaries, plates move toward each other, and something must give way. What happens depends on what types of crust are meeting. These are the places where the earth folds and recycles itself, where surface returns to depth, where the planet demonstrates its capacity for self-renewal through the patient work of geological time. Fact 15. Subduction zones, the gentle descent. When an oceanic plate meets a continental plate, the denser oceanic crust slowly descends beneath the lighter continental crust in a process called subduction. The descending plate slides into the mantle at an angle, moving downward at a few centimeters per year. As it descends, it takes water and sediments down with it, beginning a journey back into the Earth's interior. The deepest ocean trenches on Earth mark these subduction zones. Fact 16. The Ring of Fire, a circle of transformation. Around the edges of the Pacific Plate, subduction zones create a nearly continuous ring of volcanic and seismic activity known as the Ring of Fire. This isn't a place of constant chaos, but rather a vast region where Earth's internal processes manifest at the surface. Over 75% of Earth's volcanoes are found here, patiently building and rebuilding the landscape over millennia. Fact 17. Mountain building, the rise of giants. When two continental plates collide, neither can subduct because continental crust is too light and buoyant. Instead, the crust crumples and folds, pushing upward to create mountain ranges. The Himalayan mountains are still rising as the Indian plate continues its slow collision with the Eurasian plate, gaining about 5 millimeters in height each year. Mountains are monuments to the patient persistence of plate tectonics. Fact 18. Transform boundaries, the sliding dance. At transform boundaries, plates slide horizontally past each other, neither creating nor destroying crust but simply moving laterally. The San Andreas Fault in California is perhaps the most famous transform boundary, where the Pacific Plate slides northwestward past the North American Plate at about 5 centimeters per year. Over millions of years, this slow motion will carry Los Angeles up towards San Francisco. Fact 19. Pangea, the ancient supercontinent. About 300 million years ago, all of Earth's landmasses were joined together in a single, vast supercontinent called Pangea. Imagine a world where you could walk from what is now Antarctica to Africa to South America to North America without crossing an ocean. This wasn't the first supercontinent Earth has known, nor will it be the last. The continents have been assembling and breaking apart in a slow cycle throughout Earth's history. Fact 20. Panthalassa, the single ocean. Surrounding Pangea was a single, enormous ocean called Panthalassa, which covered most of Earth's surface. If you stood on the eastern shores of Pangea, you could look out across thousands of kilometers of open water, stretching uninterrupted to the horizon and far beyond. This ancient ocean has mostly been consumed by subduction, recycled back into the mantle, leaving only the Pacific as its remnant. Fact 21. The breakup begins 200 million years ago. Around 200 million years ago, Pangea began to slowly fracture. First, it split into two large landmasses, Laurasia in the north and Gondwana in the south. The rift that would become the Atlantic Ocean began to open, a crack that grew wider with each passing millennium. This wasn't a sudden shattering but a gradual, gentle separation, a continental drift that continues to this day. Fact 22. The Atlantic opens, an ocean is born. As North America and Europe pulled away from each other, and South America separated from Africa, the Atlantic Ocean slowly grew. New oceanic crust formed continuously at the mid-Atlantic ridge, pushing the continents apart at a few centimeters per year. Over tens of millions of years, a narrow seaway became a great ocean. The Atlantic is still widening today, imperceptibly spreading even as you rest. Fact 23. The Tethys Sea and ocean lost to time. Between Laurasia and Gondwana lay the ancient Tethys Sea, a tropical ocean that once stretched from what is now the Atlantic to the Pacific. As the continents continued their slow dance, the Tethys gradually closed. When Africa and India collided with Eurasia, the Tethys was consumed, its floor pushed up to form the Mediterranean Sea and mountain ranges like the Alps and Himalayas. Even oceans have finite lifespans in geological time. Fact 24. India's long journey, a continental voyage. The Indian subcontinent was once part of Gondwana, located near Antarctica. Beginning about 140 million years ago, it broke away and began a remarkable journey northward across the Tethys Sea. Moving at the relatively brisk pace of 15 centimeters per year, India traveled thousands of kilometers before colliding with Asia about 50 million years ago. This collision continues today, slowly building the Himalayas higher. Fact 25. Australia's slow drift, the isolated continent. After Gondwana broke apart, Australia drifted slowly northward, separating from Antarctica about 45 million years ago. For millions of years, it remained an isolated continent, allowing unique life forms like marsupials to evolve in isolation. Australia is still moving north at about 7 centimeters per year, and in tens of millions of years, it will collide with Asia, creating new mountain ranges in a future Earth. Fact 26. The future supercontinent Pangea Ultima. The dance of continents continues, and geologists predict that in about 250 million years, the continents will assemble once again into a new supercontinent. This future landmass has been named Pangea Ultima. The Atlantic Ocean will close, and the continents will merge in a configuration we can only imagine. Earth's face will be transformed once more, as it has been countless times before. Fact 27. The supercontinent cycle, Earth's deep rhythm. The formation and breakup of supercontinents follows a cycle lasting roughly 300 to 500 million years. Before Pangea, there was Pannotia, and before that, Rodinia, and before that, others lost to deeper time. This cycle has repeated throughout Earth's 4.6 billion year history, a slow breath of the planet, assembly and dispersal, again and again. We live in a moment between supercontinents, in a time of scattered lands. Fact 28. Volcanoes, mountains born from depth. Volcanoes are the visible expression of Earth's internal heat, places where molten rock from deep below breaks through to the surface. Most volcanoes form along plate boundaries, particularly at subduction zones and divergent boundaries. They build slowly, eruption by eruption, layer upon layer of cooled lava and ash, growing over thousands or millions of years into mountains that touch the sky. Fact 29. Hotspots, windows to the mantle. Not all volcanoes occur at plate boundaries. Some form over hotspots, stationary plumes of unusually hot mantle material that rise toward the surface. As tectonic plates slowly move over these fixed hotspots, chains of volcanoes form. The Hawaiian Islands are the most famous example, a string of volcanic islands created as the Pacific Plate passed over the Hawaiian hotspot, one island at a time, over millions of years. Fact 30. The Hawaiian Chain, a chronicle written in islands. The Hawaiian Islands tell a story of time and motion. The Big Island of Hawaii, still sitting over the hotspot, has active volcanoes. Moving northwest along the chain, each island is progressively older, having formed and then moved away from the hotspot. Kauai, the oldest of the main islands, is about 5 million years old. Beyond Kauai, the chain continues underwater as the Emperor seamounts, extending back over 70 million years. Fact 31. Shield volcanoes, gentle giants. The Hawaiian volcanoes are shield volcanoes, characterized by their broad, gently sloping profiles. They form from fluid basaltic lava that flows easily and spreads widely before cooling. These volcanoes grow slowly and steadily, eruption after peaceful eruption, building massive structures. Mauna Loa, the largest shield volcano on Earth, rises over 9,000 meters from the ocean floor, taller than Mount Everest when measured from base to summit. Fact 32. Stratovolcanoes, layered monuments. At subduction zones, a different type of volcano forms, the stratovolcano or composite volcano. These steep, conical mountains like Mount Fuji or Mount Rainier are built from alternating layers of lava and ash. The magma here is thicker and more gas-rich than at shield volcanoes, creating more explosive eruptions. But even these dramatic mountains are built slowly, layer by layer, over hundreds of thousands of years. Fact 33. Magma chambers, underground reservoirs of fire. Beneath every volcano lies a magma chamber, a vast underground reservoir where molten rock collects and slowly crystallizes. These chambers can be kilometers wide and persist for hundreds of thousands of years. The magma isn't always erupting. Most of the time, it sits quietly underground, slowly cooling, gradually rising to fill the chamber again when new magma arrives from deeper in the mantle. Fact 34. Volcanic winter, the cooling aftermath. Large volcanic eruptions can inject massive amounts of ash and sulfur dioxide into the stratosphere, where these particles reflect sunlight and cool the Earth's surface. The 1815 eruption of Mount Tambora caused the year without a summer in 1816. But such events are rare, and even major eruptions are brief moments in Earth's long climate history. The planet's systems gradually clear the ash, and warmth returns. Fact 35. Iceland born from divergence. Iceland sits astride the mid-Atlantic ridge, one of the few places where a mid-ocean ridge rises above sea level. Here, you can stand on new oceanic crust, on land that is being actively created as the North American and Eurasian plates pull apart. Iceland is also above a hotspot, making it doubly volcanic. The island grows by a few centimeters each year, pulling itself gently apart while simultaneously building upward. Fact 36. The Ring of Fire's rhythm: 75% of Earth's volcanoes. Returning to the Ring of Fire, we find a concentration of volcanic activity unmatched elsewhere on Earth. About 452 volcanoes dot the boundaries of the Pacific Plate, from New Zealand through Indonesia and the Philippines, to Japan, Kamchatka, Alaska, and down through the Western Americas. Yet even here, most volcanoes are quiet most of the time. They wait patiently, building pressure slowly, erupting occasionally, then resting again for decades or centuries. Fact 37. Earthquakes: sudden releases of slow strain. Earthquakes are sudden, but the strain that causes them builds very slowly. As tectonic plates move, friction at plate boundaries prevents smooth sliding. Stress accumulates over decades or centuries until finally, the rocks can no longer hold, and they suddenly slip. The earthquake itself lasts seconds or minutes, but it represents the release of strain accumulated over vast stretches of time. Fact 38. Elastic rebound: the bending and snapping. Imagine bending a stick slowly until it suddenly snaps. This is elastic rebound, the process behind earthquakes. Rocks on either side of a fault slowly deform as strain builds, bending like the stick. When the stress exceeds the rock's strength, the rocks suddenly spring back to their original shape, releasing energy as seismic waves. After the earthquake, the strain begins to build again, slowly, for the next event decades or centuries hence. Fact 39. Seismic waves: messages through stone. When an earthquake occurs, energy radiates outward through the earth as seismic waves. These waves travel at speeds of several kilometers per second, much faster than the tectonic plates that generate them. There are several types. P waves compress and expand rock, S waves shake it side to side, and surface waves roll along the surface. Each type tells scientists something about the earthquake and about Earth's internal structure. Fact 40. The focus and epicenter: where and what we feel. An earthquake begins at a point underground called the focus or hypocenter, where the rocks first slip. The point on the Earth's surface directly above the focus is the epicenter. Earthquakes can occur anywhere from just below the surface to over 700 kilometers deep in subduction zones. Deep earthquakes are generally less damaging at the surface, their energy dissipated through more rock before reaching us. Fact 41. The Richter scale: measuring the magnitude. The Richter scale, developed in 1935, measures earthquake magnitude based on the amplitude of seismic waves. Each whole number increase represents a 10-fold increase in amplitude and about 31 times more energy released. A magnitude 7 earthquake is major, a magnitude 8 is great, a magnitude 9 is rare and devastating. But most earthquakes are small, magnitude 2 or less, barely felt, the earth making tiny adjustments. Fact 42, the frequency-magnitude relationship, nature's balance. Small earthquakes are common, large ones are rare. For every earthquake of magnitude 7, there are about 10 of magnitude 6, 100 of magnitude 5, and so on. This relationship holds remarkably consistent worldwide. Most of the thousands of earthquakes that occur daily are too small for humans to feel without instruments. The Earth is constantly adjusting, mostly in ways we never notice. Fact 43, foreshocks and aftershocks, the sequence of events. Major earthquakes often come with smaller companions. Foreshocks are smaller earthquakes preceding a main shock, caused by the initial breaking that triggers the larger rupture. Aftershocks follow the main event, as surrounding rocks adjust to the new stress configuration. Aftershock sequences can continue for months or years, gradually decreasing in frequency and magnitude as the region settles into its new state. Fact 44, slow slip events, earthquakes in slow motion. Not all fault movement is sudden. Scientists have discovered slow slip events or silent earthquakes where faults slide over days or weeks rather than seconds. These events release as much energy as regular earthquakes but do so slowly enough that no shaking occurs. They're detected only by precise GPS measurements showing the gradual displacement. It's a reminder that even among sudden geological events, Earth has slow modes. Fact 45, intraplate earthquakes far from the boundaries. While most earthquakes occur at plate boundaries, some happen in the middle of plates. These intraplate earthquakes are less common but can be significant. The New Madrid earthquakes of 1811 to 1812 in the central United States were powerful intraplate events. They remind us that the story of plate tectonics isn't just about boundaries. Stresses propagate through entire plates, and ancient weaknesses can reawaken. Fact 46, the Himalayas still rising. The Himalayan mountain range, home to Earth's highest peaks including Mount Everest, is still growing. The collision between the Indian and Eurasian plates continues, pushing the mountains upward at about 5 millimeters per year. Everest gains roughly half a centimeter of height annually. These mountains have been rising for 50 million years, and they will continue rising for millions more, unless erosion eventually wins the battle. Fact 47, Mount Everest, the highest point. At 8,849 meters above sea level, Mount Everest is Earth's highest point. But this height is not fixed, it changes slightly with each passing year as the mountain continues to rise. The summit of Everest is made of marine limestone, rock that formed on an ancient seabed hundreds of millions of years ago. Now it stands at the top of the world, a testament to the power of plate convergence to elevate what was once ocean floor. Fact 48. The Andes, the longest mountain range. The Andes stretch for over 7,000 kilometers along the western coast of South America, making them the longest continental mountain range on Earth. They formed and continue to form due to the subduction of the Nazca Plate beneath the South American Plate. The Andes are younger than the Himalayas, having risen primarily over the last 25 million years, but they demonstrate the same principle: converging plates build mountains. Fact 49. The Alps' ancient collision, elegant peaks. The Alps of Europe formed from the collision of the African and Eurasian plates, specifically from the closure of a branch of the ancient Tethys Sea. This mountain building began about 65 million years ago and continues today, though at a much slower pace than the Himalayas. The Alps have been heavily sculpted by glaciers, which carved the elegant peaks and valleys we see today from the uplifted rock. Fact 50. The Appalachians, ancient and worn. The Appalachian Mountains of eastern North America were once as tall as the Himalayas. They formed about 480 million years ago when the continents collided to form Pangea. Time and erosion have since worn them down. Where once there were sharp peaks, now there are rounded mountains and gentle ridges. The Appalachians show us that even mountains are temporary on geological timescales, rising and then slowly, patiently wearing away. Fact 51. Erosion versus uplift, the eternal contest. Mountains rise, but they don't rise unopposed. From the moment rock is pushed upward, erosion begins wearing it down. Rain, ice, wind, and flowing water all work to level the mountains. Whether mountains grow or shrink depends on whether uplift or erosion wins this contest. In active mountain ranges like the Himalayas, uplift currently exceeds erosion. In ancient ranges like the Appalachians, erosion has long since won. Fact 52. Isostasy, mountains floating on rock. Mountains don't just sit on Earth's surface, they have deep roots extending into the mantle. Much like icebergs have most of their mass underwater. This principle is called isostasy. The thicker, lighter continental crust beneath mountains extends deep into the denser mantle below, causing the mountains to float higher. As erosion removes material from the top, the mountains slowly rise to maintain balance, like a boat rising as cargo is unloaded. Fact 53. Marine fossils on mountains, proof of uplift. Throughout the world's highest mountains, climbers and geologists find fossils of ancient sea creatures embedded in the rock. These are not anomalies but evidence of the incredible journey these rocks have taken. Limestone and shale that formed on ancient seafloors have been pushed upward, folded, and thrust to great heights. The fossils serve as markers, showing that what is now high was once deep below the sea. Fact 54. The Tibetan Plateau, the roof of the world. The collision between India and Asia created not just the Himalayas but also the vast Tibetan Plateau, an area about half the size of the contiguous United States, sitting at an average elevation of over 4,500 meters. This roof of the world formed as the crust thickened and was pushed upward. The plateau is still rising, still adjusting to the ongoing collision. It's one of the most dramatic examples of how plate tectonics can reshape entire regions. Fact 55. Ocean basins, youngest crust on Earth. The floors of Earth's oceans are constantly being renewed through seafloor spreading at mid-ocean ridges. Because oceanic crust is continuously created at ridges and consumed at subduction zones, no oceanic crust older than about 200 million years exists today. This is in stark contrast to continental crust, some of which is over 4 billion years old. The ocean floors are young, dynamic, and temporary on geological timescales. Fact 56. The Pacific Ocean, shrinking giant. The Pacific Ocean, the largest on Earth, is gradually shrinking. Surrounding it are subduction zones where oceanic crust descends back into the mantle faster than new crust is being created at the East Pacific Rise. In hundreds of millions of years, the Pacific will be much smaller, and eventually, it may close entirely as the continents continue their slow movements. Even the mightiest ocean is not permanent. Fact 57. The Atlantic Ocean, growing wider. In contrast to the Pacific, the Atlantic Ocean is expanding. The mid-Atlantic ridge creates new crust, and there are no major subduction zones consuming Atlantic seafloor. The Americas drift slowly westward while Europe and Africa move eastward. Millions of years from now, the Atlantic will be wider still, though eventually, this motion will reverse, and the Atlantic too will begin to close as the supercontinent cycle continues. Fact 58. Abyssal plains, the flattest places on Earth. The abyssal plains, vast flat regions in the deep ocean basins, are among the flattest places on Earth. These plains form as sediments from the continents and the remains of marine organisms slowly settle onto the oceanic crust, burying the rugged terrain of the seafloor beneath a blanket of fine particles. Over millions of years, these sediments accumulate, sometimes to thicknesses of several kilometers, creating smooth, featureless plains. Fact 59. Seamounts, underwater mountains. Scattered across the ocean floors are tens of thousands of seamounts, underwater mountains rising from the seafloor. Most are extinct volcanoes formed at hotspots or mid-ocean ridges. As tectonic plates carry them away from their volcanic sources, they become extinct and gradually sink as the oceanic crust beneath them cools and contracts. Some seamounts once rose above sea level as islands before sinking beneath the waves. Fact 60. Geos, flat-topped seamounts. Some seamounts have flat tops, shaped as if a giant knife sliced their peaks off. These are called geos, named after the 19th century geologist Arnold Guyot. They were once volcanic islands that rose above sea level. Wave action eroded their tops flat, and then, as the oceanic crust beneath them cooled and sank, they descended below the ocean surface. Their flat tops now lie hundreds or thousands of meters underwater, proof of their former exposure. Fact 61. The Mariana Trench, the deepest point. The Mariana Trench in the western Pacific is Earth's deepest ocean trench, reaching down nearly 11,000 meters below sea level at the Challenger Deep. This trench marks where the Pacific Plate is subducting beneath the smaller Mariana Plate. The trench is narrow, averaging only 70 kilometers wide, but it extends for over 2,500 kilometers. It's a place where the ocean floor is literally being pulled down into the earth. Fact 62. Life at subduction zones, the recycling of water. When oceanic crust subducts, it doesn't travel alone. It carries with it water trapped in sediments and chemically bound in minerals. As the slab descends and heats up, this water is released and rises into the overlying mantle wedge. The water lowers the melting point of the mantle rock, causing it to melt and form magma. This magma rises to create volcanic arcs. Thus, water from the surface returns to the surface through volcanism. Fact 63. Ophiolites, ocean floor on land. In some places, pieces of ancient oceanic crust have been thrust up onto continents during plate collisions. These formations, called ophiolites, allow scientists to study oceanic crust directly without descending to the deep ocean. Ophiolites contain the characteristic layers of oceanic crust, pillow basalts, sheeted dikes, gabbro, and pieces of the mantle. They are windows into the structure of the ocean floor, now accessible on dry land. Fact 64. The Great Rift Valley, a continent splitting. The East African Rift is a dramatic example of a continent beginning to break apart. This rift extends over 3,000 kilometers from the Afar Triangle in Ethiopia down through Kenya, Tanzania, and into Mozambique. Here, the African plate is splitting into two smaller plates, the Somali Plate and the Nubian Plate. The rift is widening at about 6 to 7 millimeters per year, and in 10 million years, a new ocean may flood this valley. Fact 65. The Red Sea, a young ocean. The Red Sea is a young ocean, born from rifting. About 30 million years ago, the Arabian Peninsula began pulling away from Africa, creating the Red Sea Rift. Seawater flooded in, and a new oceanic spreading center formed. The Red Sea is still widening at about 16 millimeters per year. It represents an early stage in ocean basin formation, showing us how the Atlantic might have looked in its infancy. Fact 66. The Dead Sea transform, sliding sideways. The Dead Sea lies along a transform boundary where the Arabian Plate slides northward past the African Plate. This is a strike-slip fault, similar to the San Andreas in California. The motion along this fault has created a depression that is filled with water to form the Dead Sea, the lowest point on Earth's land surface at about 430 meters below sea level. The fault continues to be active, with the plates sliding past each other at about 5 millimeters per year. Fact 67. Iceland's Thingvellir, walking between continents. At Thingvellir National Park in Iceland, visitors can walk through a rift valley between the North American and Eurasian plates. The valley is gradually widening as the plates separate. Vertical fault scarps show where the ground has dropped as the rift expands. It's one of the few places on Earth where a divergent plate boundary is visible on land, a tangible connection to the vast processes happening beneath our feet. Fact 68. The San Andreas Fault, California's Great Divide. The San Andreas Fault runs roughly 1,200 kilometers through California, marking where the Pacific Plate grinds northwestward past the North American Plate. The two plates slide past each other at about 50 millimeters per year. Over the past 20 million years, this motion has carried coastal California hundreds of kilometers northward. Millions of years from now, Los Angeles will be a suburb of San Francisco, carried by the patient, persistent sliding of stone against stone. Fact 69. Baja California, an island in the making. The Baja California Peninsula is slowly being torn away from mainland Mexico by the same tectonic forces driving the San Andreas Fault. The Gulf of California, also known as the Sea of Cortez, is a young rift where new oceanic crust is forming. In millions of years, Baja California will be completely separated from Mexico, becoming an island moving northward with the Pacific Plate, a future Hawaii-like archipelago in a reconfigured Pacific Ocean. Fact 70. Mountains and weather sculpting climate. Mountain ranges created by plate tectonics profoundly influence global and regional climate patterns. The Himalayas, for instance, block cold air from Central Asia from reaching the Indian subcontinent, while also forcing moisture-laden air upward, creating the monsoon rains. Mountains wring water from passing air masses, creating wet climates on windward slopes and rain shadows on leeward sides. Plate tectonics shapes not just the land but the very air that flows over it. Fact 71. Chemical weathering, mountains eating carbon. When mountains rise, they expose fresh rock to the atmosphere. Rainfall, slightly acidic from dissolved carbon dioxide, slowly dissolves minerals in the rock in a process called chemical weathering. This process consumes CO2 from the atmosphere and eventually locks it away in ocean sediments. The uplift of the Himalayas over the past 50 million years may have helped cool Earth's climate by accelerating this carbon removal, demonstrating how the solid Earth and atmosphere are intimately connected. Fact 72. Volcanic gases adding to the atmosphere. While weathering removes carbon dioxide from the atmosphere, volcanic eruptions add it back. Volcanoes release water vapor, carbon dioxide, sulfur compounds, and other gases from Earth's interior. Over geological time, volcanism has been essential in maintaining Earth's atmosphere and oceans. The carbon cycle involves both the removal of CO2 by weathering and its return through volcanism, a balance maintained over millions of years. Fact 73. Continental positions affecting ice ages. The positions of continents influence Earth's climate. When continents are positioned near the poles, as Antarctica is today, ice sheets can form and grow. Antarctica hasn't always been ice-covered. It was much warmer when it was part of Gondwana and located farther north. The continent drifted to its current polar position about 35 million years ago, and only then did its massive ice sheet begin to form. Continental drift sets the stage for ice ages. Fact 74. Ocean currents, guided by geography. Plate tectonics determines the shape of ocean basins and the positions of continents, which in turn control ocean currents. The opening of the Drake Passage between South America and Antarctica about 41 million years ago allowed the Antarctic circumpolar current to form, thermally isolating Antarctica and contributing to its glaciation. The closure of the Isthmus of Panama about 3 million years ago altered Atlantic and Pacific Ocean circulation, affecting global climate. Fact 75. The carbon cycle, Earth's thermostat. Plate tectonics drives Earth's long-term carbon cycle, which acts as a planetary thermostat. When Earth warms, more rainfall increases chemical weathering, removing more CO2 and cooling the planet. When Earth cools, reduced weathering allows volcanic CO2 to accumulate, warming the planet again. This negative feedback system, operating over hundreds of thousands to millions of years, has helped keep Earth habitable throughout its history. The slow movement of plates maintains this balance. Fact 76. Snowball Earth, when the system faltered. Despite the stabilizing carbon cycle, Earth has experienced periods when it became almost entirely ice-covered, known as snowball Earth episodes. The most recent occurred between 720 and 635 million years ago. Even then, volcanic activity continued beneath the ice, gradually adding CO2 to the atmosphere. Eventually, enough greenhouse gas accumulated to break the freeze, and Earth thawed. Plate tectonics kept the planet alive during its deepest freeze. Fact 77. The Deccan Traps, massive volcanic province. About 66 million years ago, enormous volcanic eruptions in what is now India created the Deccan Traps, a massive plateau of basaltic lava covering over 500,000 square kilometers. These eruptions coincided with the extinction of the dinosaurs and may have contributed to environmental stress through volcanic gases and climate change. The eruptions were likely triggered as the Indian plate passed over the Réunion hotspot. Even catastrophic events occur through the mechanisms of plate tectonics. Fact 78. Large igneous provinces, times of great outpouring. The Deccan Traps are one example of large igneous provinces, lips, enormous volcanic events that have occurred periodically throughout Earth's history. These events release vast amounts of lava and gas over relatively short geological periods, 1 to 5 million years. Several mass extinctions coincide with lips, suggesting that plate tectonic processes can sometimes push Earth's climate system beyond the limits that life can tolerate, though life has always recovered. Fact 79. Igneous rocks born from fire. Plate tectonics drives the creation of igneous rocks, those formed from cooling magma. At mid-ocean ridges, basaltic magma cools to form oceanic crust. At subduction zones, different magmas rise to create volcanic rocks like andesite. Deep within mountain belts, slow cooling produces granitic rocks. Every igneous rock carries information about where and how it formed, a record of tectonic processes written in mineral grains. Fact 80. Sedimentary rocks, layers of time. Erosion of mountains created by plate tectonics produces sediments that accumulate in layers, eventually forming sedimentary rocks like sandstone, shale, and limestone. These rocks often contain fossils and preserve records of ancient environments. When continents collide, these sedimentary rocks can be lifted high into new mountains. The limestone at the summit of Everest was once mud and shells on an ancient seafloor, transformed through the patient work of tectonic forces. Fact 81. Metamorphic rocks, changed by pressure and heat. When rocks are buried deep within the earth, especially in mountain building zones or subduction zones, heat and pressure transform them without melting them, creating metamorphic rocks. Shale becomes slate, then schist, then gneiss. Limestone transforms into marble. These rocks record the intense conditions within active plate boundaries. When erosion eventually exposes them at the surface, they reveal the deep processes that have shaped continents. Fact 82. The rock cycle, never-ending transformation. Plate tectonics drives the rock cycle, the continuous transformation of rocks from one type to another. Igneous rocks weather into sediments, sediments compact into sedimentary rocks. These are buried and become metamorphic rocks. Metamorphic rocks melt to form new igneous rocks. At each stage, plate movements provide the necessary conditions. Convergent boundaries create heat and pressure for metamorphism. Divergent boundaries generate igneous rocks, and uplift exposes rocks to weathering. Fact 83. Recycling the crust, Earth's efficiency. Through subduction, oceanic crust that formed at mid-ocean ridges returns to the mantle, sometimes carrying with it sediments, water, and even pieces of continental crust. This material is recycled, melted, and eventually returns to the surface through volcanism. Over billions of years, material has cycled repeatedly through Earth's crust and mantle. The atoms in the rocks beneath your feet may have been part of ancient continents, ancient ocean floors, ancient volcanoes. Fact 84. Continental crust formation, building the continents. Continental crust is created primarily at subduction zones. When water-rich oceanic crust descends into the mantle, it releases fluids that cause the overlying mantle to melt. This magma is less dense than oceanic crust and rises to form volcanic arcs. Over time, these arcs collide with continents, adding new material. Continents have grown slowly throughout Earth's history through this process, building the platforms where terrestrial life flourishes. Fact 85. Cratons' ancient stable hearts. At the core of most continents lie cratons, ancient, stable regions of continental crust that have not been significantly deformed for billions of years. These are the oldest parts of continents, some dating back over 3 billion years. Surrounded by younger mountain belts and sedimentary platforms, cratons are the durable remnants of ancient tectonic processes, having survived multiple supercontinent cycles. Fact 86. Wilson Cycle, the life of an ocean. The Wilson Cycle, named after Canadian geophysicist John Tuzo Wilson, describes the life cycle of an ocean basin. It begins with rifting, like the East African Rift, proceeds to a young ocean, like the Red Sea, then a mature ocean, like the Atlantic, then begins to close as subduction begins, like the Pacific, and finally closes completely in a continental collision, like the ancient Tethys. After collision, the cycle can begin again. Oceans are born, grow, and die in a rhythm spanning hundreds of millions of years. Fact 87. Plate tectonics and biodiversity, creating habitats. The movement of continents creates and destroys barriers to migration, profoundly affecting evolution and biodiversity. When Pangea existed, terrestrial species could migrate freely across vast distances, leading to relatively uniform fauna. As Pangea broke apart, populations became isolated on separate continents, evolving independently. Australia's unique marsupials, South America's distinct mammals, and the special character of each continent's life all reflect their tectonic journeys. Fact 88. Island formation, laboratories of evolution. Volcanic islands created by hotspots or at convergent boundaries serve as isolated laboratories for evolution. When organisms colonize these islands, they evolve in isolation, often developing into unique species found nowhere else. The Galapagos Islands, formed by volcanic activity over a hotspot, hosted the finches and tortoises that helped Darwin develop his theory of evolution. Every volcanic island is a potential cradle for new species. Fact 89. Mass extinctions, tectonic connections. Several of Earth's mass extinctions have been linked to tectonic events. The eruption of massive flood basalts, driven by deep mantle plumes, coincided with the end Permian extinction, 252 million years ago, the end Triassic extinction, 201 million years ago, and others. Continental collisions altered climate and ocean circulation. While plate tectonics can stress life, it also creates opportunities, opening new habitats and driving evolutionary innovation. Fact 90. Hydrothermal vents, oases in the abyss. At mid-ocean ridges, seawater seeps down through cracks in the newly formed oceanic crust, is heated by magma below, and erupts back into the ocean as superheated hydrothermal vents. These vents support unique ecosystems based not on sunlight but on chemosynthesis, where bacteria derive energy from chemicals in the vent fluids. These may resemble the environments where life first evolved. Plate tectonics creates these oases in the deep sea. Fact 91. Nutrients from erosion feeding the oceans. Mountains raised by plate tectonics are sources of nutrients. Rivers eroding these mountains carry minerals and elements to the sea, where they fertilize oceanic life. uplift of the Himalayas increased erosion rates, delivering more nutrients to the oceans and potentially supporting more productive marine ecosystems. The nutrients that support ocean food webs, from phytoplankton to whales, trace back to mountains born from colliding continents. Fact 92. Oxygen and early life, continental shelves. The formation of continental shelves, the shallow underwater extensions of continents, may have been crucial for the evolution of complex life. Shallow, sunlit waters on these shelves supported abundant photosynthetic organisms that produced oxygen. The Great Oxidation Event about 2.4 billion years ago transformed Earth's atmosphere, enabling the evolution of complex, oxygen-breathing life. Continental configuration in shallow seas, shaped by plate tectonics, set the stage. Fact 93. Climate stability and habitability, the Goldilocks condition. Earth's plate tectonics may be essential for long-term habitability. The carbon cycle driven by plate tectonics has kept Earth's climate within a range suitable for liquid water for billions of years, despite the sun growing brighter. Venus and Mars, lacking active plate tectonics, have not maintained habitable surface conditions. Earth's restless surface, constantly renewing itself, may be why life has flourished here for so long. Fact 94. Measuring plate motion, GPS in the present. Today, scientists use GPS satellites to measure plate motion with millimeter precision. We can watch continents drift in real time, confirming the predictions of plate tectonic theory. These measurements show that the rates calculated from geological records match current motion. The North American and Eurasian plates separate at about 2.5 centimeters per year. The African and South American plates pull apart at about 3 centimeters per year. The ancient dance continues, now directly observable. Fact 95. Future Earth 50 million years hence. Looking forward 50 million years, Africa will have collided with Europe, closing the Mediterranean Sea and creating a new mountain range. Australia will have moved significantly northward toward Asia. The Atlantic will be wider, the Pacific narrower. The East African Rift will have opened into a new ocean. California will have moved northward along the San Andreas Fault. These predictions are as reliable as any long-term forecast can be, based on current plate motions. Fact 96. Future Earth 250 million years hence. In 250 million years, the continents may again assemble into a supercontinent, perhaps Pangea Ultima. The Atlantic Ocean will close as the Americas collide with Europe and Africa. Antarctica might drift northward. A single, vast ocean will dominate Earth's surface. New mountain ranges will rim this supercontinent. And then, inevitably, this supercontinent will break apart again, continuing the cycle that has repeated throughout Earth's history. Fact 97. The slowing dance Earth's eventual stillness. Plate tectonics requires heat from Earth's interior. As our planet ages, it cools, and eventually, there will not be enough heat to drive mantle convection. plate tectonics will slow and eventually stop. Earth will become geologically quiescent, like Mars. This won't happen for perhaps 1 billion years or more, but it is Earth's eventual fate. The dance that has shaped our world for billions of years will come to rest, and Earth's surface will finally still. Fact 98. Other worlds, Earth's uniqueness. Earth is the only planet we know with active plate tectonics. Venus may have had plate tectonics in its past, but its surface shows no current activity. Mars is too small and cold, its lithosphere too thick. The icy moons of Jupiter and Saturn have dynamic surfaces, but not plate tectonics as we know it. Earth's active surface, constantly renewing itself, may be rare in the universe. We live on a remarkable world. Fact 99. Gratitude for restlessness, a moving planet's gifts. We might wish for a stable, unchanging world, but Earth's restless nature is a gift. Plate tectonics creates diverse habitats, drives the carbon cycle that stabilizes climate, recycles nutrients, and may be essential for life's long-term survival. The earthquakes and volcanoes that sometimes threaten us are consequences of the same processes that make Earth habitable. Our moving planet is not despite its dynamic nature but because of it. Fact 100. The story continues tomorrow and forever. As you drift off to sleep, the dance continues. Plates move their imperceptible distances. Mountains rise grain by grain. Ocean floors spread and sink back into the mantle. Continents journey slowly across the globe. This story has no ending, only continuous transformation. The earth beneath you is not fixed but flowing, not static but in constant, patient motion. And in this endless movement, there is something deeply peaceful, the knowledge that change, even dramatic change, unfolds slowly, gently, in the fullness of time. And so our journey through the story of plate tectonics comes to rest, though the story itself never ends. The continents will continue their slow voyage, the ocean floors will spread and return to the depths, mountains will rise and erode away, all in the vast expanse of geological time. As you sleep, the earth moves beneath you, patient and persistent, engaged in the ancient dance that has shaped our world for billions of years and will continue for billions more. Rest now, knowing that the planet itself is in constant, gentle motion, that change is the only constant, and that even the mightiest mountains and deepest oceans are temporary visitors on Earth's ever-changing face. Sleep well, and dream of deep time. Thank you for watching Sleepy Science Post. Sweet dreams, and may your rest be as peaceful as the slow drift of continents.